In section 2.3, we look at functions. Functions is a topic that is probably review for many of you, but we will go ahead and go over it thoroughly here to make sure that you all have a solid foundation. So first we start with the definition of a relation. A relation establishes a correspondence between two sets of numbers, set A and set B, such that for each element in A, there is at least one corresponding element in B. So a relation is exactly what it sounds like. It's a relationship between two sets of numbers such that there is some kind of a correspondence that assigns an element of set B to every element of set A. Now, I won't spend a lot of time talking about relations. I could give you a few examples of this, but instead we're just going to get right into functions. So a function is a correspondence between set A and set B, just like a relation, such that for each element in A, there is exactly one corresponding element of B. So notice that in the definition of a relation, it says there is at least one corresponding element in B. For a function, there has to be exactly one element in B. So we have a nice little picture here that kind of shows you a diagram of what it means to be a function. And what you can see here is that we have this set A, which consists of 4 elements, and those elements are just these dots that you see right here. And then in set B, you'll see these little squares over here, and those are the elements of set B. So what we can see here is that in set A, this first dot here gets assigned to this square over here. And this second dot here gets assigned to this square over here. And this third dot gets assigned to this square here. And this fourth dot gets assigned to this square here. So notice that for every single one of the elements of A, I only assigned one element of B to that element of A. Now, you will notice that if you look at these two elements, they go to the same output value, but that's okay. That doesn't violate something being a function, okay? What you can't have happen is you can't have the same element in set A going to two different elements in set B. So we'll be talking about some examples here, and once we go through some examples, I think you'll have a better understanding of what it means to be a function. Before we go to those examples, let's also talk about another way we can think about a function. So we can think of the set A that I referred to on the previous page as the set of all input values, and set B is a set of all output values. And so if X is an element of A, so that's an input value, there is exactly one corresponding output value, which we call f of X, which is an element of B. Now, the letter f is just the name of the function. And of course, we use f because the word function starts with the letter f. But we don't have to use the letter f. We could use some other letter to name our function. The quantity f of X is pronounced just as I said it, f of X, or f at X. And the parentheses here does not represent multiplication. So this diagram kind of describes what's going on here. A function takes an input value, an X value, you put it into the function, and the function does something to it by whatever mechanism it has, and it prescribes an output value, and we call that output value f of X. So what's happening is the function is kind of like a machine. You put something into this machine, and the function transforms it into something else when it comes out of the machine. So another way to kind of diagram this is you put an X value into the function, and the function takes that X value and transforms it into another value. Okay, and again, the X here is our input value, the f of X is our output value. So the variable X can refer to any one of the possible input values and usually is referred to as the independent variable. And the corresponding output value that we call f of x is usually referred to as the dependent variable. Most of the time, functions are defined by formulas. However, functions do not always need to be defined by formulas. They can be given as a table or a graph, or they can be simply described in words, all right? So we're going to go through some examples where you can see the various ways that we can talk about a function. So in our first example here, we just want to check the definition of a function. Which of the following correspondences here satisfy the definition of a function? So in our first example, part A here, we have the input value is the set of these letters, J, F, M, A, S, O, N, D. And the output value is the name of a month beginning with that letter. And the question is, does this represent a function? So let's go ahead and draw the set here representing all the input values and the set over here representing all the output values. In the first set, we are going to have all of the letters, so J, F, M, A, S, O, N, and D. And in the second set, we're going to have all of the months of the year. So here we have all of those. Now what we need to check is, do each of the elements of the first set go to exactly one element of the second set? And I'm going to go out of order here on purpose. So if we take the letter F, for example, the letter F can only represent the month of February, right? Because February is the only month that begins with the letter F. The letter S can only represent the month of September. O can only represent October. N can only represent November. And D can only represent December. But when you get to J, M, and A, notice that for M could represent March, and it could also represent May, right? So this one letter of the first set is getting assigned to two different members of the second set. That right there alone tells you that this is not a function, okay? But furthermore, look at J. J could represent the month of January, it could represent the month of June, or it could represent the month of July. And finally, A could represent April, or it could represent August. So we have multiple elements of the first set that go to multiple elements of the second set. So this first correspondence here is not a function. All right? Let's check out the others. So in the second example, part B, it says the correspondence defined by table 1. So for part B, we are looking at this table here, and it's a little different. They don't tell us what the input values represent. They don't tell us what the output values represent. But notice that you have 5 different input values, and you have the corresponding output value. So the input value, -4, gets assigned to the output value of 0.5. The input value of -3 also gets assigned to 0.5. 0 gets assigned to 0.5. 2.5 gets assigned to 0.5. And 13/2 gets assigned to 0.5. Does this represent a function when all of the elements of the first set go to the same element of the second set? And the answer is yes. This is a function. What can't happen is you can't have the same element of the first set going to 2 different elements of the second set. So it's perfectly fine for every element here to go to the same output value. That's not a problem according to the definition of a function. Let's take a look at the third one. So in the third one here, it says the input value is the radius of the circle and the output value is the area of the circle. So let's think about circles. So if I have a circle like this and the radius is some value r, let's say, we should all know that the area of a circle is pi times the radius squared, right? It's a very common formula from geometry. Now, if you have a particular input value, what is the output value going to be? So let's just imagine a few of these possibilities here. What if the radius of the circle is 2 centimeters? Then according to the formula, the area would be pi times 2 centimeters squared, which would be pi times 4 square centimeters, and that is 4 pi square centimeters. So when I have a radius of 2 centimeters, notice that the output value for the area is 4 pi square centimeters. So I had one input value and it gave me exactly one output value, right? It's not possible for the area to be something different from 4 pi when the radius is 2, right? There's only one possibility. Let's think of another possibility. What if the radius of the circle was 5 feet? Then what would the area be? Well, according to the formula, it's pi times 5 feet squared. And this would be pi times 25 square feet. And pi times 25 is 25 pi, and that would be square feet. So once again, a single input value gave us a single output value. And it's not too hard to see that for every number that you plug in for r, you will only get one number for the area. So the answer here is yes, this is a function. So in our next example, we're going to get a little bit more mathematical now. For these functions, we're going to assume that f of x, the function, is defined by the equation x squared minus 1. And we just want to evaluate the following. So let's talk about this real quick. When we say f of x is equal to x squared minus 1, this is the same as saying y equals x squared minus 1. So in other words, x is our input value. So when you have a number for x, you're going to plug that in, you're going to square it, and then you will subtract 1. And that's going to give you your output value, which we often call f of x in the case of a function. That's the same as saying if I plug in a value for x and I do this to it, that's going to give me a value of y. So for functions, it is often convenient to remember that f of x and y are essentially the same thing. F of x is just a new name for the variable y, okay? So let's remember that y is the same as f of x. All right, now let's get into these examples. So in part A, they ask us to find f of negative 2. So again, f of x is x squared minus 1. So if I'm looking at f of negative 2, what I'm doing is I'm replacing x with negative 2. So negative 2 is the value of the independent variable. And to calculate the dependent variable, I'm going to substitute negative 2 in for x in the equation here. So this gives us negative 2 squared minus 1. Negative 2 squared, remember, that's negative 2 times negative 2, which is positive 4, and then minus 1, that's 3. So the answer is 3. In the end, I can write f of negative 2 is equal to 3. And what we're saying is when the value of the input variable is negative 2, the output of the function is positive 3. So remember that this is your input value, and this is your output value. To put that a slightly different way, your input value is x, your output value is y, or f of x. Okay, let's do the next one. So next we have f of 1/2. So this works the same way. It's going to be 1/2 squared minus 1. If we do the math on that, remember 1/2 squared is just 1/2 times 1/2. 1/2 times 1/2 is 1/4. And 1/4 take away 1 is negative 3/4. So the summary here is f of 1/2 is equal to negative 3/4. Let's try the next example, part C. For part C, they ask us to find f of x plus 1. So this is a little bit different. So keep in mind, we have the rule for our function right here. The rule says f of x is x squared minus 1. So f of x plus 1 means that I'm going to replace the x here with x plus 1. And that means I need to replace the x on the other side with x plus 1. So according to the rule for this function, this is equal to x plus 1 squared minus 1. And this is x plus 1 times x plus 1 minus 1. And to finish this, we need to multiply this out. So we'll go ahead and do that. This is going to be x squared plus 1x plus 1x plus 1. And then don't forget, you still have minus 1 here. Combining like terms, we get x squared plus 1x and 1x is 2x. And then the plus 1 and the minus 1 cancel each other out. So we end up with this. So in summary, f of x plus 1 ends up giving us x squared plus 2x. So notice that when you plug a variable into a function, you just get a new function. All right, the next one we have on the list, I know it's off screen here, but it was f of the square root of 5. So again, just go back to your original definition of the function, which is right here. F of the square root of 5 is going to equal the square root of 5 squared minus 1. So that's going to be radical 5 to the second power minus 1. Well, when you square a radical, those cancel out and you just get 5 there. So this is 5 minus 1, which is 4. So f of the square root of 5 is equal to 4. That's the summary of the result there. Okay? And the last one we have is to find f of x cubed. So let's do that last one there. So again, remember that f of x is equal to x squared minus 1. So in part E, we are finding f of x cubed. And again, it just means that we are replacing x with x cubed. So if I replace the x right here with x cubed, we get x cubed quantity squared minus 1. And then we can use properties of exponents. When you have a power to a power, you multiply those powers, and that gives us x to the 6 minus 1. Okay, so f of x cubed is x to the 6th minus 1. So again, the takeaway here is that when you plug a number into a function, you get a function. When you plug a variable into a function, you get, when you plug a number into a function, you get a number. When you plug a variable into the function, you get a new function. Okay, so let's just try a couple more examples here just to make sure that we understand what's going on. So for example 3, they want us to evaluate g of negative 3 and g of a squared for the following functions. So in part A, g of x is the square root of 1 minus x divided by 2. So when they ask us to do g of negative 3, again, we are just replacing x with negative 3. So that means I'm going to plug negative 3 in for x on the other side. So when I do that, that's going to give us the square root of 1 take away negative 3, quantity divided by 2. Do the math here. 1 minus minus 3 means 1 plus 3. And that's the square root of 4. And that's 2, and then don't forget to divide by 2, so in the end we get 1. So again, g of negative 3 is 1. So when I plug a number into a function, I get a number. Now, what about the second part, g of a squared? Well, g of a squared, same thing. You're going to take the x in your function and you're going to replace it with a squared. So when we do that, we get the square root of 1 minus a squared divided by 2. And that's all we can do there. We cannot simplify this radical, so this is our answer. So again, the takeaway here is that when you plug a variable into a function, you get a new function, right? Compared to when you plug a number into a function, you get a number. All right, let's look at the second part there. So for part B, we have g of x is equal to x plus 4 divided by x minus 2. And the first we want to do here is g of negative 3. So g of negative 3 says we are going to plug negative 3 in for x. So that means each one of these x's here on the other side gets replaced with negative 3. So that's negative 3 plus 4 divided by negative 3 minus 2. Negative 3 plus 4 is 1. Negative 3 minus 2 is negative 5. And 1 divided by negative 5, we're going to change that to negative 1/5. So g of negative 3 is negative 1/5. Once again, when you plug a number into a function like this, you get a number out of it. And for the second part, g of a squared, again, we are going to take the function g of x, and we're going to replace x with, in this case, a squared. So when we do that, on the right-hand side, we get a squared plus 4 divided by a squared minus 2. And again, there's nothing that we can do there to simplify that, so this would be our answer for the second part. And again, you plug a variable into a function and you just get a new function. Now let's talk about piecewise defined functions. So we've already seen an example of a piecewise defined function before when we talked about the definition of an absolute value function earlier. So let me remind you that the absolute value of x is equal to x if x is a non-negative number, and the absolute value of x is equal to negative x if x is a negative number. And so, for example, if x is negative 3, since negative 3 is a negative number, the absolute value of negative 3 would use this definition. So it's equal to negative 3, which of course turns into positive 3. But if x was equal to positive 3, then the absolute value of 3 would simply be 3, because since 3 is a positive number, we would use this part of the piecewise defined function. So in a piecewise defined function, you basically have multiple functions, and you have to decide which one to use depending on what they tell you about when to use it. Okay? So let's take a look at the example below here for more understanding. So here we have a function h of x is equal to the number 1 if x is less than 0. It's equal to the function negative x plus 1 if x is a number between 0 and 2. And it's equal to negative 3 if x is a number bigger than 2. So what we want to do is take this definition of a function and find the following function values. So if you're asked to find, for example, in part A, h of 2, you have to know which of these are you going to use. Well, remember, this value here is an x value. So we have to say, which one do we use when x is 2? Well, we don't use the first part because that's only true if x is less than 0. We don't use the last part because that's only true if x is bigger than 2, right? And 2 is not bigger than 2. So that means we're going to use the middle one. Now, why are we using the middle one? Well, if you focus in on that definition right there, it tells you use the middle one when x is a number between 0 and 2, including 2. So that's why we're going to use this definition. So what is h of 2? Well, according to that definition, it is negative x, so that's going to be negative 2 plus 1, and that is negative 1. Okay, so again, all I'm doing there in the end is I'm replacing x with 2. So that's how we get negative 2 plus 1. Let's look at part B. Part B says, what is h of negative 6? Well, when you have negative 6, where does that fall into? Which of these categories? Well, it falls into the first category, right? Because negative 6 is a number that is less than 0. So what is h of negative 6? Well, you're supposed to use this definition. Well, what this tells us is that if x is a number that's less than 0, h of x is just equal to 1. There's no x to plug into here. This is a constant function. So h of negative 6 is 1. And finally, for part C, it says, what is h of 0? Well, let's see. Do we use this definition? No, because that's only true when x is less than 0, so that's out. Do we use this definition? Well, this is only true if x is bigger than 0, but less than or equal to 2. But if x is bigger than 0, that does not mean x is 0. So no, we don't use that. And finally, we can't use this one either, because if x is bigger than 2, it can't be 0. So what this tells you is this definition of a function does not prescribe a function value for when x is 0. So what we would say here is that h of 0 is undefined, right? Because there's no part of the function that accounts for the value when x is 0. Now let's talk about a couple of other really key concepts, and that is the concept of the domain of a function and the range of a function. So the domain of a function is just simply the set of all input values for which the function will produce a real number. And the range of a function is a set of all output values which correspond to at least one element in the domain of the function. So a simple way to think about domain and range is the domain is the set of all input values, and input values we usually call x, and the range is the set of all output values, and the output values is what we usually call y. All right? Now, the range can be a little bit tricky, so let's go ahead and go through these examples to see if we understand the concept of domain and range. So for each of these functions, we want to find the domain, and then we want to write it in interval notation. Okay, so our first function here is g of t is equal to t squared plus 4. So the domain is the set of all values we can plug in for the variable t in this case, right? Because t is your independent variable here. So the question you really want to ask when you're trying to find a domain is, are there any restrictions? So what does it mean to be a restriction? Well, remember the things that you can't do if you want to get a real number. So one is you cannot divide by 0, right? And the other one is you cannot take a square root of a negative. Okay, those are the two things you can't do. So any number that's going to give you a square root of a negative or is going to result in dividing by 0 is not a number that you can plug into a function. But if you look at the function t squared plus 4, there is no division, right? So you will never be dividing by 0, no matter what number you plug in. Also, there is no square root, so you don't have to worry about taking the square root of a negative. So you are free to plug in any number you want for t. So the domain for this first function is t can be any real number. So another way to say that is the domain is the set of all real numbers. And then we want to write that in interval notation. Well, we should know that the set of all real numbers in interval notation is the set from negative infinity to positive infinity, because basically we're saying we can plug in any number on the real number line. Okay? So that's a pretty simple one. You can see in the remaining examples, all of the remaining examples have division and they also have square roots. So we're going to have to be a little bit more careful in these upcoming examples. So for part B, we have f of x is equal to the square root of 4 minus x. And we want to know, what is the domain? What are the x values that you are able to plug in? Okay, so I'm going to do this intuitively at first, and then I'll show you a mathematical way to do it. So let's think about what we can and can't plug in. Let me just make a little table of values here. And we'll go ahead and get right to it. Can I plug in the number 4? Well, if you plug in the number 4, you're going to end up getting the square root of 4 minus 4, which is the square root of 0, and the square root of 0 is 0. So there's no problem with that. When you plug in 4, you get 0. Okay, so we can plug in 4. Can you plug in 3? Well, if you plug in x equals 3, you get the square root of 4 minus 3, which is the square root of 1, which is 1. So remember, as long as you're taking the square root of a positive, we have no issue here. So when I plug in 3, I get the number 1. Well, it's not too hard to see that I can plug in 2, right? I can plug in 0. I can even plug in x equals negative 12, right? Think about that. Can I plug in x equals negative 12? Well, if I do, I get the square root of 4 minus negative 12. That's the same as the square root of 4 plus 12, which is the square root of 16, which is 4. So no issues there. So what can't I plug in? Well, I can't plug in any number that's going to give me a negative on the inside of the radical. So for example, I cannot plug in 5. If I plug in 5, I have the square root of 4 minus 5, which is the square root of negative 1. And yes, that's equal to I, but remember, we define the domain to be those numbers that give us real numbers. Okay, so I cannot plug in 5. Can I plug in 6? No, right? If I plug in 6, I get the square root of 4 minus 6, which is the square root of negative 2. So I can plug in 4. I can plug in anything less than 4, but I cannot plug in anything greater than 4, right? Even 4.1 is no good, because if I plug in 4.1, I get the square root of 4 minus 4.1, and that's the square root of negative 0.1, right? And that's no good because that's an imaginary number. So what are the numbers that I can plug in? Again, I can plug in 4, or I can plug in any number less than 4. So my domain is x has to be a number that is less than or equal to 4. And you can write this in set notation. The way this looks in set notation is you say the set of all x such that x must be less than or equal to 4. And that's just kind of a fancy way of writing it. But more importantly, we want to write this in interval notation. So let's remember that on a number line, if this is the number 4, and you're plugging in any number less than 4 or equal to 4, in interval notation, this would correspond to the numbers from negative infinity up to 4. All right, let's take a look at the next one. So for part C, we have the function h of s is equal to 1 over s minus 1. So there are no square roots in this one, but we do have division. And I think it's pretty simple to see that if you try to plug in 1, right, h of 1 would be 1 divided by 1 minus 1. And that would be 1 divided by 0, and 1 divided by 0 is undefined. So you cannot plug in the number 1. Now, 1 is the only number that will give you 0 in the denominator, right? So 1 is the only restriction. So the domain here is all real numbers except x equals 1. And a way to put that in interval notation, we can plug in any number that is less than 1. We can plug in any number that is greater than 1, but we cannot plug in 1 itself, so we have an open circle there. And in interval notation, that would be negative infinity up to 1, not including, union 1 to infinity. This is how we would write the domain in interval notation. And that's really a complicated way of saying x cannot be 1. And for the final one here, we have the function h of t is equal to 1 over the square root of 4 minus t. Now, I mentioned that I was going to show you an algebraic way to do part B. I didn't do that, but I'll do it for part D instead so that we can see a more efficient way for doing this problem. Okay, so let's take a look at what the function is here. 1 divided by square root of 4 minus t. We have two things happening here. Number one, we cannot plug a negative into a square root, so t has to be a number that doesn't give us a negative in here. And number two, this number inside the square root also cannot be 0, because if it's 0, the square root of 0 is also 0, and then we will be dividing by 0. Okay, so what I'm saying is 4 minus t must be positive, right? It cannot be negative, right? Whatever's inside the radical cannot be negative, but it also cannot be 0. So what I'm really saying here is 4 minus t must be greater than 0. That's what it means to be positive. So all I have to do is solve this inequality for t. And I could do that by subtracting 4 from both sides. And when we subtract 4, we get negative t is greater than negative 4. And then I'm going to divide both sides by negative 1. And when I do that, I get t here, I get 4 here. And then remember, the inequality has to reverse anytime you divide by a negative. So in order for us to get a real number in this function, we can only plug in values of t that are less than 4. And on a number line, here's 4. If t has to be less than 4, it looks like this, and there's an open circle there. So that is all the numbers from negative infinity up to 4. That's our domain. And just want to come back to the definition of a range here. Notice that we didn't talk about the range for any of those functions. The range can be kind of challenging, and we'll be talking more about the range in the next section when we start looking at graphs of functions. All right, let's go ahead and go on to our next example. So here we have an example modeling weekly pay. It says Eduardo is a part-time salesperson at Digitex Audio, a sound equipment store. Each week, he is paid a salary of $200 plus a commission of 10% of the amount of sales he generates for that week in dollars. What are the input and output variables for this problem? Okay, so we're looking at Eduardo's salary. We're going to have our input values, which we're going to call X, and our output values, we can call those Y, or we could call those f of X. I'll call it f of X. And I just want to describe what are these values represented or representing in this problem. Okay, well, what determines Eduardo's salary is the amount of sales that he generates, right? He gets 10% commission on the amount that he sells. So, for example, if he sells $3,000 worth of equipment, his commission is going to be 10% of that, which is going to be $300. So what determines his salary is this. It's the amount that he sells. Okay, that's our input value, X. So the input value, X, is the total amount of sales in dollars. The output value, f of X, is going to be Eduardo's salary, right? Okay, so that's part A. Part B now says, express Eduardo's pay for 1 week as a function of the sales he generates that week. Okay, so what is his pay going to be? So let's remember that his pay is going to be $200 no matter what. He gets a fixed salary no matter what he sells. But on top of that, he also gets 10%, which is 0.10, multiplied by the amount of sales that he generates. So if X is the total amount of sales in dollars, he gets 10% times X, and that gets added to his $200. So as a function, we could say f of X is equal to 200 plus 0.10 times X. And then we would just understand that this is in dollars. And then for part C, it says, what was his pay for a week in which he generated $4,000 worth of sales? So they're telling us that X is $4,000. So his pay is going to be F of $4,000, which is $200 plus 0.10 times $4,000. And if you do the math on this, this is $200 plus 10% of 4,000 is $400, and this is a total of $600. In the next example, we have a function that is given by a table, and it says that Table 3 gives the U.S. Postal Service's rate for a first-class letter, this is in 2013, as a function of the weight of the letter in ounces. Letters heavier than 3.5 ounces are classified separately and are not listed here. So, same as before, in Part A, we want to identify the independent variable and the dependent variable. So the independent variable is this one here. It is the weight in ounces. Okay, so the independent, they call that W for weight, and this is the weight of the letter in ounces. And the dependent variable, which is just the output value, that's going to be the rate. We'll call that R for rate, and that's basically going to be the cost of sending the letter. Part B, explain why this table represents a function. Okay, well, if you have a letter weighs a particular amount. No matter what the weight of your letter is, that's going to fall into one of these categories. And once you know what category it falls into, you can see the rate that they charge right here. So if, for example, the weight was 1.5 ounces, 1.5 is a number between 1 and 2, that would cost 66 cents. So because your weight is only a single number, that means it's only going to fall into a single category. And then once you get that category, there is a single rate. So every unique weight has a unique postage amount, okay? So that's a verbal explanation. And finally, for part C, what is the rate for a first-class letter weighing 3.2 ounces? Well, 3.2 ounces is a number in between 3 and 3.5. So the rate there is 1.06. So $1.06 to send a letter that weighs 3.2 ounces. And our final example, here we have a function given by a graph. So this graph has the months of the year as the independent variable, and then the average temperature during that month as the dependent variable. And this is for the city Fargo in North Dakota, and this is in degrees Fahrenheit. So what they say is let T of M be a function represented by the graph where M is the month of the year and T is the temperature, okay? So in part A, they ask you, what is T of May? So one thing I want to point out here is notice that for this function, you're not actually plugging in a number for your independent variable. Your independent variable in this case is a month of the year. So all they're asking here is, what is the average temperature in May? So I identify May on the graph, and if I go up to the height here and take that directly across, it appears that the average temperature in May is somewhere around 70 degrees Fahrenheit. Okay, so that's going to be the answer that I give, 70 degrees Fahrenheit. And notice that I can't give a precise value here because when you're looking at a graph, you just can't always give precision. And then for part B, it says, what are the valid input values for this function? Well, the input values are the values of the independent variable, and those are simply the months of the year. Okay, so January, February, March, April, May, June, July, August, September, October, November, December, those are the input values for this function. So most of the time in this class, our functions are going to be mathematical. Okay, they're going to have an equation associated with it, like you saw in some of the previous examples. But functions don't have to be purely mathematical in nature. They could be given by a chart or a table. And so you need to have an open mind to accept all the different ways that functions can be given to you.